Good morning, everyone. Welcome to the day three of Julia programming. In last 2 days, we have discussed about uh, in last 2 days we have discussed about variables and integers and floating point numbers and mathematical operation and elementary functions and complex and rational numbers and strings and functions and control flow. Today we will discuss about the scope of variables and types and methods, and if time permits, then I will also discuss about constructor and converter and promotion and modules. Okay, and rather than these three topics, after scope of variables, types, and methods, I will directly jump to the section of probability, introduction to probability and machine learning, like how we can use Julia for these two topics. For these two topics, I will just follow up some examples which I have already precompiled in my system. Let's talk about scope of variables. First, let me share my screen. Yeah. So in Julia, the scope of a variable is the region of code within which a variable is visible. And variable scoping helps avoid variable naming conflicts. The concept is intuitive. Two functions can both have arguments called x without the two x referring to the same thing. Similarly, there are many other cases where different blocks of code can use the same name without referring to the same thing. So the rules for when the same variable names does or doesn't refer to the same thing are called scope rules. Okay. Certain construct in the language introduce scope blocks, which are regions of code that are eligible to be the scope of some set of variables. So the scope of variable cannot be an arbitrary set of source lines. Instead, it will always line up with one of these blocks. There are two main types of scopes in Julia, which are global scope and local scope. The letter can be nested. There is also a distinction in Julia between constructs which introduce a hard scope and those which only introduce a soft scope, which affects whether shadowing a global variable by the same name is allowed or not. Okay. Now directly I will jump to some these of examples which I have already compiled in my environment. So today, as you will notice, today I am using Jupyter Notebook instead of Pluto or VS Code or Julia Raphael. If you want to use Jupyter Notebook, then just open Jupyter Notebook in your local computer and directly go to where in your browser the localhost will open. Okay, then directly come here and then click on new, and on new just select which Julia version you want to use. These Julia versions are already installed in my local computer, so that's why you are able to see four types of Julia versions. The recent Julia version is Julia 1.6.0, which I am using since last 3 to 4 months. Okay, so right now I am using Julia 1.6.0. So just click on Julia 1.6.0 and it will directly open a new Jupyter notebook. Okay, where you can run your examples, like whatever you have to run. Okay, so now let's directly jump to over this section. Okay. As Julia uses lexical scoping, meaning that a function's scope does not inherit from its caller's scope, but from the scope in which the function was defined. For example, in the following code, the x inside foo. Okay, in the following example, the x inside foo refers to the x in the global scope of its module bar. Okay, and not a x in the scope where foo is used. Okay, and then I imported this var module which I have defined here, and I defined a variable x is equals to -1 and then var dot foo. Okay, so here the lexical scope means that what a variable in a particular piece of code refers to can be deduced from the code in which it appears alone and does not depend on how the program executes. Okay, so a scope nested inside another scope can see variables in all the outer scope in which it is contained. Outer scopes, on the other hand, cannot see variables in inner scope. Okay. Now I will talk about global scope. So each module introduces a new global scope separate from the global scope of all other modules. So there is no all encompassing global scope. Okay. So modules can introduce variables of other modules into their scope through the using or import statements, as you can see here. Um, so module can introduce variables of other modules into their scope through the using or import statement or through qualified access using the dot notation. Okay, this dot notation. So note that like while variable bindings can be read externally, they can only be changed within the module to which they belong as an escape hatch. So you can always evaluate code inside that module to modify a variable. Then this guarantees in particular that module bindings cannot be modified externally by code that that never calls evil. Okay. So here I have here I am talking about global scope. So I defined a module A, and I assigned the variable age equals to 1, which is a global in module A scope. Okay, and then here I defined a module B, and inside module B I also called a module C, and then I defined a scope like C is equals to 2, and end of this module. Okay, then I again here it can access the namespace of a nested global scope through a qualified access. Okay, and here it makes module A available. Okay, so here you will note that interactive prompt is in the global scope of module main. Okay, and now I will talk about local scope. So a new local scope is introduced by most code blocks. Some programming language require explicitly declaring new variables before using them. Explicit declaration works in Julia too. Okay. It is like in any local scope, writing local x declares a new local variable in that scope, regardless of whether there is already a variable named x in an outer scope or not. So declaring each new local like this is somewhat verbose and tedious. So however, so Julia, like many other languages, considers assignment to a new variable in a local scope to implicitly declare that variable as a new local. Okay, so mostly this is pretty intuitive, but as with many things that behave intuitively, so the details are more subtle that one might naively imagine. So here Julia applies the following rules to decide on what the expression means based on where the assignment expression occurs and what X already refers to at that location. So the first rule is existing local. So if X is already a local variable, then the existing local X is assigned. And second one is hard scope. So here if X is not already a local variable and assignment occurs inside inside of any hard scope construct within a lat block, so function or macro body or comprehension or generator. So then in this case, a new local named X is created in the scope of the assignment. And the third one is soft scope. So if X is not already a local variable and all of the scope construct containing the assignment are soft scopes. Okay. Uh, So here now B will begin with a nice and clear-cut situation as where like assignment inside of a hard scope. So in this case, a function body when no local variable by that name already exists. Okay, so here I am talking about local scope. Here, if you will see inside of the greet function, okay, the assignment y is equals to hello causes y to be a new local variable in the function's scope, in this function's scope. Okay, so there are two relevant facts. The assignment occur in local scope, and there is no existing local y variable since y is y is local, so it doesn't matter if there is a global named y or not. So here, for example, now I defined y is equals to 1 to here I defined x is equals to 1 to 3 before defining and calling greet. Okay, so as you can see here, before defining and calling greet, I already defined x is equals to 1 to 3, so it will call a global scope. Okay, so now since the x since here the x is in greet, okay, so which is local, so the value of the global x is unaffected by calling a greet. So the hard scope rule doesn't care whether a global named x exists or not. So assignment to x in a hard scope is local unless x is declared global. Got it? So the next clear-cut situation, like now we will consider, is when there is already a local variable named x, okay, in which x is equals to x will be some value which will always assigns to this existing local x. So in this case, here the function sum to it will compute like which computes the sum of the numbers from 1 up to n. Okay, so here, like as in previous example, the first assignment to S, as like in this example, the first assignment to S at the top of sum, the function sum2 causes S to be a new local variable in the body of the function. So here the for loop has its own inner local scope within the function scope. So at the point where s is equals to s plus I occurs, s plus I occurs, so s is already a local variable here. Okay, so s is already a local variable here for I. What mistake I made here? Oh, s is equals to s plus I and assign as existing local. So I was telling like here s equals to s plus I already occurs. So s is already a local variable. So the assignment updates the existing x instead of creating a new local. So now we can test this out of calling function sum2 in the repile. Okay. So now in this case, if you will see, yeah. So here, since like s is local to the function sum2, calling the function has no effect on the global variable s. So now we can also see that the update s is equals to s plus I in the for loop must have updated the same as created by the initialization s is equals to 0. Since we get the correct sum of 55 for the integers 1 2 through 10. Okay, now let's take into the fact like that the for loop body has its own scope for a second by writing a slightly more verbose variation which we will call sum to which we are calling here sum to def in which we save the sum s plus I in a variable t. Okay, before updating s. So this version returns as okay as before, but it also uses the at is defined macro to return a boolean indicating whether there is a local variable named named this t, defined in the function's outermost local scope. Okay, so as you can see, there is no t defined outside of the for loop body. Okay, so as we have not defined t outside of this for loop body. So this is because of the hard scope rule again, since the assignment to T occurs inside of a function which introduces a hard scope. So the assignment causes T to become a new local variable in the local scope where it appears. So inside of the loop body, even like if there were a global named T, it would make no difference. So the hard scope rule isn't affected by anything in global scope. So now let's move on to some ambiguous cases which will cover by the soft scope rule. Okay, so now here we will explore this by extracting the bodies of the grid and sum to depth function into soft scope context. So first let's put the body of grid in a for loop. Okay, so first let's put the body of grid in a for loop which is soft rather than hard, and let's evaluate it in this repile. Okay. So here, as you can see here, since the global x, oh sorry, here I have taken a variable k, not x. Since this global x, it is global k, sorry, not x. Okay. So here, since global k is not defined when the for loop is evaluated. Okay, so the first clause of the soft scope rule applies and k is created as, and here k is created as local to the for loop and therefore global k. This global k remains undefined after the loop executes. So now next let's consider the body of sum to depth function which will sum to depth which will be extracted into global scope, fixing its argument to n is equals to 10. Okay. So here, what does this code do? So it's like a tricky question. So the answer is it depends. If the code is entered interactively, it behaves the same way it does in a function body. But if the code appears in a file, so in that case, it prints an ambiguity warning and throws an undefined variable error. So let's see it working in the repile first. Okay. So here I initialize s is equals to 0, which is our global scope. Okay, then I define a for loop, and inside for loop I defined a variable rt inside the local scope, and then I assigned that t in variable s. Okay, and then I again called this and then I again defined a global variable s. Okay. So in this case, the repile approximate being in the body of a function by deciding whether assignment inside the loop assigns to a global or creates new local based on whether a global variable by that name is defined or not. So if a global by the name exists, then the assignment updates it. Okay, then if the global so then the assignment will update it, and if no global exists, then the assignment creates a new local variable. So in this example, we can see both cases in action. So there is no global named t, as you can see here. There is only local t. So t is equals to, so in this case, t is equals to s plus I creates a new t that is local to the for loop. And then there is a global named s. So s is equals to t assigns to it. Okay. So the second fact is why execution of the loop changes the global value of the global value of s, and the first fact is why t is still undefined after the loop executes. So now let's try evaluating this same code as though it were in a file instead. So here we put the same code in a file like inside a triple quite string, okay, which I described in the previous session. Okay, here like I used include a string to evaluate code as though it were the contents of a file. Okay, so now we could also save this code to a file, and then we can directly call include on that file to go our repile. Let's say if we are saving this code into a file, let's call the file name is something example.jl, and directly we can call this file here something like this, including and example.jl, and you will have to give the exact path for this particular file, as I have not defined any file like this. So if you will run this, so then it will execute some error. As you can see, a system error, opening file, no such file or directory, because it is not able to file something named example.jl file in my directory team poison. Got. So I was telling like here I used include a string to evaluate code as though like it were the contents of file. So now we could also save code to a file and then call include on that file. So the result would be the same. Now as you can see, this behaves quite different from evaluating the same code in the repile. Let's break down like what's happening here. Okay, so here global s is defined with the value 0 before the loop is evaluated. Okay, so the assignment s is equals to t occurs in a soft scope. Okay, a for loop outside of any function body or other hard scope construct. Therefore, the second clause of the soft scope rules applies, and the assignment is ambiguous. So a warning is emitted. Okay, and then execution continues, making as local to the for loop body, and then like since s is local, since s is local to the for loops, then it is defined when t is equals to s plus I is evaluated, when this expression is evaluated. T is equals to s plus I. So then like here it is causing an error. Then like here evaluation stops. Like what if it got to s, and at the rate is defined t is defined macro variable t, then like it would return 0 and false. So this demonstrate like some important aspects of a scope. In a scope, like each variable can only have one meaning, and that meaning is determined regardless of the order of expression. Okay, so the presence of the expressions as a equals to t in the loop causes s to be local to the loop, which means that it is also local when it appears on the right hand side of t is equals to s plus I, even though that expression appears first and is evaluated first. And one might imagine like that the s on the first line of the loop could be global, while the s on the second line of the loop is local. But that's not possible, since the two lines are in the same scope block and each variable can only mean one thing in a given scope. Okay, so now I will talk about on a soft scope. Okay, so on soft scope. So now we have now covered of the like all the local scope rules. But before wrapping up this section, like I have a few words to say about why the ambiguous soft scope case is handled differently in interactive and non-interactive contexts. So there are two obvious questions like which you can ask, which are why doesn't it just work like the repile everywhere? Okay, and the second question is why doesn't it just work like in files everywhere and like maybe skip the warning? So in Julia version before the Julia version 0.6, okay, all global scopes did work like the current repile. So when x is equals to some value occurred in a loop, or try or catch or struck body, but outside of a function body, then like it was decided based on whether a global named x was defined or not, whether x should be local to the loop. So this behavior has the advantage of being intuitive and convenient, since it approximates the behavior inside of a function body as closely as possible. So in particular, it makes it easy to move code back and forth between a function body and the REPL when trying to debug the behavior of a function. But here is some downsides. First, it's quite a complex behavior. Many people over the years were confused about this behavior and complained that it was complicated and hard both to explain and understand. So it was a fair point. And the second one was and arguably worse. Okay, is that it's bad for programming at scale. Like when you see a small piece of code in one place like this, it's quite in something like this. S is equals to 0 for I is equals to 1 to 10, then S plus I and end of the loop. Okay, so it's quite clear what's going on here. Obviously, this intention is to modify the existing global variable x. What else could it mean? However, not all real world code is so short or so clear. We found that code like the following occurs in the wild. Oh, okay. So now let's have a look on this. So here I am defining and for I is equals to 1 to 10, x is equals to hello, and print ln x and end of the loop, and then again y is equals to x plus 234. Okay, so here it is far less clear what should happen here, since here x plus hello. Okay, is a method error. It seem probable that the intention is for x to be local to for the for loop. Okay, so but runtime values and what methods happen to exist cannot be used to determine the scope of variables. So with the Julia version 0.6, this behavior, it's especially concerning that someone might have written the for loop first, okay, had it working just fine, but later when someone else adds a new global far away, possibly in a different file, the code suddenly changes meaning and either breaks noisily or bursts still, silently does the wrong thing. So the kind of spooky action at a distance is something that good programming language designs should prevent. Okay, so in Julia version 1.0, they simplified the rules for scope. So then in any local scope assignment to a name that wasn't already a local variable, created a new local variable. So this eliminated the notion of soft scope entirely, as well as removing the potential spook for spooky action. Then here we uncovered and fixed a significant number of bugs and due to the removal of soft scope and vindicating the choice to get rid of, and there was much rejoicing well, no, not really, because some people were angry that they now had to write something like this. S is equals to 0 and for y is equals to 1 to 10, and global s uh, I and end of the loop. So here, do you see that global annotation in there? So it was very hideous. Obviously, this situation could not be tolerated. But seriously, there are two main issues with requiring global for this kind of top level code. The first one is it's no longer convenient to copy and paste the code from inside a function body inside the REPL to debug it. You have to add global annotations and then remove them again, then again to go back. Okay. So the second one is beginner will write this kind of code without the global and have no idea why their code doesn't work. So in this case, the error they get is that S is undefined, okay, which does not seem to enlighten anyone who happens to make this mistake. So now, as of Julia 1.5 or later version, this code works without the global annotation in interactive context like the REPL or Jupyter notebooks, just like it was working Julia the version 0.6. And in files and other non-interactive contexts, it prints this very direct warning. Assignments to S in soft scope is ambiguous because a global variable by the same name exists and S will be treated as a new local. So disambiguate while using local S to suppress this warning or global S to assign to the existing global variable. So this addresses both issues while preserving the programming at scale benefits of the 1.0 behavior. Global variable have no spooky effect on the meaning of code that may be far away. So in the REPL, a copy and paste debugging works and beginners don't have any issue. Anytime someone either forgets a global annotation or accidentally shadows an existing global with a local in a soft scope, which would be confusing anyway. So they get a nice clear warning. Okay. An important property of this design is that any code that executes in a file without a warning will behave the same way in a fresh repile and on the flip side. So if you take a repile session and save it to file, if it behaves differently than it did in the repile, then you will get a warning. Okay. And now I let's talk about let blocks. So, unlike assignments to local variable, LED statements allocate new variable bindings each time they run. So, an assignment modifies an existing value location, and LED creates new location. So, this difference is usually not important and is only detectable in the case of variables that outline their scope via closure. So, here the LED syntax accepts a comma separated series of assignments and variable names. So let's do something like this. Here I'm assigning some variables x, y, z um, to the values, and then let block x is equals to 1 comma z println x is that uh, then we will have to put inside this block, not outside inverted commas. Here x is local variable and y is the global variable. Okay, and then again print ln z, and here the error will occur errors as z has not you will face error because as z has not been assigned yet what is local and end of this block. Okay. So when you will run this, then you can see here, as I had told you, here x is local variable and y is the global variable, and the error occur because as has not been assigned yet, but it is local. Okay. So the assignments are evaluated in order here, like which each right hand side evaluated in the scope before the new variable on the left hand side has been introduced. So therefore, it makes sense to write something like let x is equals to x, since the two x variables are distinct and have separate storage. So here is a, like now I am giving an example where the behavior of let is indeed. So fs vector, any vector, okay, undefined 2 and I is equals to 1, and let's run a loop here while I is less than or equals to 2. um, fs of course I, uh, something like this, which is pure to I, not outside of this square brackets, and global I is equals to I plus 1, and end of this while loop. And let's call the index for this variable fs1. Okay, and now again fs2. So for fs2, so here like a b created and stored two closure that returns variable I. However, it is always the same variable I, so the two closures behave identically. Here, as you can see, like here, the two closures are behaving identically. So now we can use let to create a new binding for I. So let's use let to create a new binding I for fs is equals to any vector, and if 2 I is equals to 1. Oh, it's vector, not vector. Okay, and then let's define the while loop again. While I is less than or equals to 2, let I is equals to 1, fs I, fs I, and of this let block, and then global I is equals to I plus 1, end of this while loop. So here if you will, so now you won't get identical. What is taking that much time to run this? Oh, while let I equals to I not 1. रन हो जाएगा ये. Let's delete this cell first. Now let's call it capital FS. Oh, Why this code block is taking that much time? Is my session ended? Let I everything is fine here. And let's try to run the same thing in the Julia Raphael session. I'm not able to figure it out like why it is taking that much time. So fs any vector and I equals to 1, and then let's define a while loop while I is less than or equals to 2. Let I is equals to I and fs I end of this let block and global I is equals to I plus 1 end of this while loop. Okay. So now if you will call this fs1 and again fs2. Okay. Yeah. So here, as you can see, since the begin construct does not introduce a new scope, so it can be useful to use a zero argument let to just introduce a new scope block without creating any new bindings. Okay. So now let's first have a look like it's working or not. X is equals to 2 network. Not really because I have two sessions. I am not getting like a why it is not working. Anyway, let's move forward further. I will have a look on this problem later. Let's try to create a new Julia. And let's close the previous ones. Okay. Now let's try if it is working or not. Okay. Okay, now I will continue in this notebook. Okay, so till now, I will talk about loops and comprehensions. So in loops and comprehensions, are new variables introduced in their body scope. In their body scopes are freshly allocated for each loop iteration, as if the loop body was surrounded by a lead block. Like now, let's demonstrate this by the given example. So let's fs some vector, any any vector, and let's run a loop here for j is equals to 1 to 2, and fs j end of this loop. Now let's iterate it over the index fs index 2. So here, like a for loop or comprehensive iteration, here as you can see, um, here the new here a new variable introduced in the body scopes and was specially allocated for each loop iteration. Okay, so because like here the for loop and now let's talk about a for loop or comprehensive iteration variable is always a new variable. However, like okay, yeah. So now let's talk about constant. So a common use of variables is giving names to specific unchanging values. Such variables are only assigned once. So this intent can be conveyed to the compiler using the constant keyword. Constant keyword. So which is like a const is equals to some value. Let's call it something like this. Okay, so something like this. We can define a constant. Okay, so the constant declaration should only be used in global scope on global. So it is difficult for the compiler to optimize code involving global variables, since like their values might change at almost any time. So if a global variable will not change, so adding a constant declaration solves this performance problem. Okay, so it was all about constant. Okay, now I will talk about types. So in Julia, type systems have traditionally fallen into two quite different camps. So static, which is like a static type systems, where like every program expression must have a type computable before the execution of the program. And the second one is dynamic type systems. So in dynamic type systems, like it is known about types until runtime. So when the actual values manipulated by the program are available. So object orientation allows some flexibility in statically typed languages while letting code be written without the precise types of values being known at compile time. So the ability to write code that can operate on different types is called polymorphism. Okay, so in this case, like all code in classic dynamically typed language is polymorphic on like it will be polymorphic only then like only by explicitly checking our types or when objects fail to support operations at runtimes. But like here, the Julia's type system is dynamic because but gains some of the advantage of static type system by making it possible to indicate that certain values are of specific types. Okay, so now I will talk about type declaration. So to for type declaration, we use this operand, this operator. Okay, these two column. I don't know why what we call it right now. I am not So the this operator like can be used to attach type annotations to expressions and variables in programs. So there are two primary reasons to do this. The first reason is as an assessor to help confirm that your program works the way you expect. Okay, and the second reason is to provide extra type information to the compiler, which can then improve performance in some cases. When appended to when it will be appended to an expression computing to value, so this operator is read as is an instance of. So it can be used anywhere to assert that value of the expression on the left is an instance of the type on the right. So when the type on the right is concrete, the value on the left must have that type as its implementation. So recall that all concrete types are final, so no implementation is a subtype of any other. So when the type is abstract, so it suffices for the value to be implemented by a concrete type that is a subtype of the abstract type. So if the type assertion is not true, so then in that particular case, an exception will be thrown. So here I am talking about types. So what I was telling, like if the type assertion is will not be true, so then in that particular case, an exception will be thrown. Otherwise, the left-handed value will be returned. So, for example, 1 plus 2, and we are saying like it the type is abstract float. Okay, when you will run this block, then here you will get an exception because it expected it will be an abstract float, but it got a value of type int 64. As you can, it got the value of type int 64, but we define the type abstract float. So that's why it throw error. So an exception was thrown here. Okay, now like if you will define the type int, then it won't throw any exception here, and it will give you the output. So this allows the type assertion to be attached to any expression in place. Okay, so when appended to a variable on the left hand side of an assignment, when appended to a variable in the left hand side on the left hand side of an assignment, or as part of a local declaration, so this operator. Okay, this operator means something a bit different. It declares the variable to always the specified type, like a type declaration in a statically typed language such as C. So every value assigned to the variable will be converted to the declared type using convert. Now let's see another example here. I am defining a function foo, and inside this function I define the variable x. The type of this variable x should be int 8. Okay, and then I return an end of this function. So let's call this. So here if you will check the type of this variable, type of x. So here as you will get, the type of this variable is int 8. Okay. So this feature is useful for avoiding performance gotchas, like that could occur if one of the assignments to a variable changed its type unexpectedly. So this declaration behavior only occurs in like a specific context, something like this. Local x int 8. It should be the like here in a local declaration. In local DICL in a local declaration. Okay, and here as the left hand side of an assignment. So here it is syntax type local declaration. So here like it applies to the whole current scope, even like a before a declaration. Currently type declaration cannot be used in global scope, as you can see. Here as you can it is saying like the type declaration on global variables are not yet supported. Okay, now a declaration can also be attached to function definitions. Okay, let's say I am defining a function sin c, and I'm defining a type. The type is float 64, and if I'm assigning, it will return 1 and return sine pi into x, divided by pi into x, and end of this function. Okay, so returning from the function behaves just like an assignment to a variable with a declared type. So the value is always converted to float 64. Like let's say if you are passing sin c some uh, sine 10, then it will be always converted to a float 64 value. Okay, so now the second thing is abstract types. So abstract types cannot be instantiated, and like it serve only as nodes in the type graph, like thereby are describing sets of related concrete types, those concrete types which are their descendants. So now be like here we begin with abstract types, even though like they have no instantiation, because they are the backbone of the type system. They form the conceptual hierarchy, which makes Julia's type system more than just a collection of object implementation. Got it? Now I will talk about primitive types. Like there are some other types as well, which are primitive types and composite types. In primitive types, like there is a warning, like it is almost always preferable to wrap an existing primitive type in a new composite type than to define your own primitive type. So this functionality exists to allow Julia to bootstrap the standard primitive types that LLVM supports. So once they are defined, there is very little reason to define more. So to define a primitive type, you can do something like this: primitive type float 16 and abstract float 16 and of this type. Oh, okay. So something like this, you can define a primitive type. Okay. And now the second type is composite types. So composite types are called records, structs, or objects in various languages. So a composite type is a collection of named fields, an instance of which can be treated as a single value. So in many languages, composite types are the only kind of user-definable type. And they are by far the most commonly used user-defined type in Julia as well. Okay, so composite types are introduced, like here I will introduce the composite types with struct keyword followed by a block of field names, optionally annotated bit types using this operator. Okay, so let's define a composite type: struct foo bar z, it should be int, var should be int, and qqx, it should be a type of float 64, and end of this struct. Oh, again. So fields with no type annotation are annotation default to any, and can accordingly hold any type of value. So it was all about composite types and primitive types. Okay, and now I will talk about mutable composite types. Okay, so if a composite type is declared with mutable struct instead of struct, okay, here as I let's here I will call with here I will declare with mutable struct. Okay, then instances of it can be modified. Okay, in case of mutable. So let's first declare it with mutable struct bar and bars QQX float 64 and end of this. Okay, and now let's call bar hello 1.5. Oh, okay, and now let's call var dot qqx 2.0. Okay, then it will give the output 2.0. And again, if you will call var dot bars, let's give it a rational number. As I told you, if you will just for rational number, you will have to put two for backward slash. Okay, then you will get a rational number here. Okay, so now in order to support mutation, such objects are generally allocated on the heap. Okay, and have stable memory addresses. So a mutable object is like a little container that might hold different values over time, and so can only be reliably identified with its address. So in contrast, an instance of an immutable type is associated with a specific field value. So the field values alone tell you everything about the object. In deciding whether to make a type mutable ask or whether two instances with the same field values would be considered identical, or if they might need to change independently over time. Okay. Um, Now, like there is declare types and declare type unions. So for type unions, you will just call a union and you will give in that type int or abstract strings. Okay. Now there is a parametric types. In parametric types, we just give the parameters. Okay, to the variable. Something like this. Is struct for parametric types. So struct point t parameter t and xt and yt and end of this block. So here the declaration defines first let me tell you about a parametric composite type. So type parameters are introduced immediately like after the type name surrounded by the curly braces. Okay. So in this case, this declaration defines a new parametric type point t. Okay, holding two coordinates of type t, which is x and y. What one may ask, like, is t like a well? Like, what is t? Like you can ask. So, well, that's precisely the point of parametric types. It can be any type at all, or a value of any bits type. Actually, although like here it's clearly used as a type. So, point float 64 is a concrete type equivalent to the type defined by replacing capital T in the definition of like. It was all about parametric composite types. And now, what I can discuss here, uh, yeah, now I can discuss about parametric abstract type. If you have defined parametric abstract type, then how you can do. So in this case, parametric abstract type declarations declare a collection of abstract types. Okay, something like this. Abstract uh, type point t. So it is parametric abstract types. Okay. And Yeah, so there are tuple types as well. So for tuple types, you have to do something like this. Struct tuple to A, comma B. So it is a tuple types. Okay. So in tuple types, we have a hierarchy tuple types, like the where the last parameter of tuple type can be the special type of hierarchy. Okay, like which will donate any number of trailing elements. And another one is name tuple type. So in name tuple types, name tuples are instances of the name tuple type, which has two parameters: a tuple of symbols giving the field names, and a tuple giving and a tuple type giving the field types. And union all types, singleton types. So you can find more types in the Julia documentation itself, I guess. If you will go to the Julia website, then here is the documentation. So you can see the manual as well to know more about type. Like it in base, like they have explained all about like whatever they have implemented to develop this language. Okay. So to know more about types, just please follow the documentation. And now what can be the another topic right now? Yeah, so it was all about types and scope of variables. So now I will follow up some examples here, which was remaining in the last session. So what where are those examples? So here I have added more examples. Okay, so the last example I had discussed was about image processing. Okay, now I will talk about uh, now I will follow this random walks examples. Okay, so in this example, if you will see the line 3 to 21. Okay, define the function path as first argument. It takes a random generator R and G. Okay, so that is the function is designed to receive an object such as a machine twister as an argument. Okay, machine twister as an argument, and this second argument is alpha, and the third argument is the number of steps in the path with a default value of 5,000. Okay, and then again in line 6 to 19, in line 6 to 19, we loop n times, each time updating the current coordinate x and y, and then pushing the values into the arrays xz and yz. Okay, and then line 7 generates a random value in the range 1 to 4. And now, which observes the use of RNG as a first argument to rand function. Okay, to rand function, and then again in line 13 to 15, I multiplied rand RNG by 2 plus alpha. So this creates uniform random variables in the range 0 to 2 plus alpha. Okay, and line 20 again. Then here line 20 returns a tuple of two arrays, xdat and bydat. Okay, then after setting alpha range in line 23 and setting default plotting arguments here in line 25, these are the default plotting arguments. Okay, so I created plot paths with common random variables in line 26. Oh. So in line 26 and line 28, this is because in each call to path function, I used the same seed to a newly created machine twister. Okay, a machine twister object. So here 27 is just an arbitrary starting seed. This number 27 is just an arbitrary starting seed. In contrast, now line 31 to 33 have repeated calls to path using a single stream RNG, like created in line 30, here created in line 30. Okay, and hence here I don't have common random numbers because each subsequent call to path function to this path starts at a fresh point in the stream of RNG. Now let's run this example. If you want to run block by block, then you will have to press Alt plus Enter. Then it will just run block by block in your BS code. And then here you can see the result. Okay, in line 35, we combine all the plots which we get from line 26 to 28 and from 31 to 33. So this example was about uh, random box. Okay, now let's say if you want to call some packages from Python language and R. Okay, so let's say if you are solving some machine learning problem and you have not that package available in Julia. So in that particular case, you can also call that Python package inside your Julia environment. So let's see an example for that. So to call any Python package, okay, in a Julia environment, first you should install that Python package in your local environment. So or then like after installing then that package, then you can call that package using a package which is available in Julia and which is known as PyCall. Okay, so to use PyCall, first you will have to install that in your Julia environment. So it is already installed in my environment. When you will click, when you will add PyCall, then you will get like no changes because it is already installed in my environment. So after installing that package, let's wait for a while. Okay, then now call this package using PyCall. Okay, and after calling that package, you will have to set your Python environment in Julia. And how you can do this? You can do this something like this: environment Python, and then your Python path. And then how you can know the Python path? Then you will call here Python, then Like I am calling here Python just using Python. So I can just directly mention here Python. I don't need to mention my whole path. Okay, in this case. So now I have set this path. Okay. Now after setting the environment, you will have to build this package. So how you can do this? Just go to this mode, package mode. Okay, after entering into the package mode, call command build and package name, which is pycall. So after building that package, now you can call any Python inside your Julia program. Okay, so let's say in my example, I am using a Python package named as text blob. So first, I will have to install this package. So how I can do this? Pip install uh, text blob. So now it will install this package here. So let's wait for a few sec. Okay, so here I am providing a brief example like which makes use of a text blob Python library, which provides a simple API for conducting natural language processing tasks, including part of speech tagging, noun phrase extraction, sentiment analysis, classification, translation, and more. So for our example, I use TextBlock to analyze the sentiment of several sentences. So the sentiment analyzer of TextBlock outputs a tuple of values, with the first value being the polarity of the sentence. Okay, and the second value a rating of subjectively. Okay, so now I have installed the this package as well, and now I have built PyCall as well. I have set it the environment as Python environment as well. So now I can directly come to our example. After doing this, now let's run this. After running, I will explain what is going on here. Let's run the rep file again. Okay, so in this example, like you will see the line 2. In line 2, the import function is used to wrap the Python library text blob. Okay, like to use any Python library, first we will have to wrap that library inside Julia. Okay, so like which is then given the Julia alias TV, I wrap this library inside a variable called TV. Okay, so now from line 4 to 9, the string is created. So for this example, the string is written as a first hand account and contains many words that give the text a negative tone. So if you will note the use of multi-line strings using triple quote. Okay, so now in line 11, here in line 11, so in line 11, the text blob function from TV, okay, is used. So this function is used to parse each sentence in string, okay, in this str variable. So the output is stored as blob. So this is where the call to Python is made. And then in line 12, a comprehension, then in line 12, a comprehension is used to print the sentiment field for each sentence in blob. And now if you will note that sentiment is a Python-based field name, which is accessible via Julia. So as stated in the text blob documentation, the sentiment of the blob is field name is as an ordered pair of polarity, and subjectively with polarity measured over a domain of -1 to plus 1. Okay, very negative to very positive, and subjectively over 0 to 1 means very objective to very subjective. So the results here indicate that the first sentence, like when you will see the result, so the result will indicate like that the first syntax is the most positive, but is also the most subjective, while the last sentence is the most negative, but also more subjective. Now let's run it and let's see the result here. Mm, using by call and then build by call. Let's wait for some second here. Now let's run it again. Now why it is not reporting it? Here is a path error in my case, but like if you will give the right path as I had told you when you will set the environment, then it will run for surely. Okay, so you can check this on your own now. And the same thing goes with R as well. Okay, so in R, like I have not installed R in my environment right now, so I won't be able to call any R package. So but the procedure is same as like we have followed in the Python. First, you will have to set the environment for your R compiler. After setting, then when you will install the R packages, then just run this example, then it will work for sure. Okay, here I am using three types of data, which is already stored in my this directory data folder. So from here I am reading these three files. Okay, got it. So now let's move on to the next problem, which is birthday problem. and it is something related to probability. Okay, so in this example, here I am considering a room full of people. Okay, then like I am asking, what is the probability of finding a pair of people that share the same birthday? So obviously, ignoring a leap years, let's say if there are 366 people present, then it happens with certainty via the pigeonhole principle. Okay, if you know about pigeonhole principle, then I guess you will pick this problem like soon. Okay, but I won't be discuss about pigeonhole principle. Okay, but however, what if there are fewer people? Okay, so in like then like it can be interesting. With about 50 people, a birthday match is almost certain, and with 23 people in a room, there is about a 50% chance of two people sharing a birthday, and at first glance, this non-intuitive result is surprising, and hence this famous probability example earned the name the birthday paradox. However, I just refer to it as the birthday problem. So now to carry out the analysis, now there are some mathematical things which I won't discuss, but I just named it as birthday problem, and I just told you the problem, what is the problem and what we are trying to get. So now I will directly move on to our code. Okay. So first I will just simply run this code, then I will discuss this code block by block. That what I have done here. Okay. So here, if you will see here, I have used three packages, which are state space and combi networks and floats. Okay, these three packages I have already installed in my environment. Okay, so and then again in line 3 and 4, two alternative functions for calculating the probability are defined. Okay, in here are two alternative functions, which is match exist 1 and match exist 2 are defined. Okay, and so the first uses the plot function to apply a product over a comprehension. So this is in fact a numerically stable way of evaluating the probability, and the second implementation evaluate in a much more explicit manner. It uses the factorial function, okay, from the combinatorics package, and note that the basic factorial function is included uh, in Julia base. However, the method with two arguments comes from the combinatorics package. Also, the use of a big function. First, let me minimize this thing. Okay, so here also the use of big function ensures the input argument is a big int type. So this is needed. Why this is needed? It is needed to avoid overflow for non-small values of n. And then from line 6 to 10, it defines the I define the function BD event which simulates a room full of n people, and if at least two people share a birthday, okay, then it returns true. Otherwise, it will return false. Okay, and now we now explain how it works. Okay, so line 7 creates the array birthdays of length n. Okay, so now line 7 creates the array um, birthdays of length n, and uniformly and randomly assigns an integer in the range 1 to 365. Okay, in the range 1 to 365 to each index. So the values of this array can be thought of as the birth dates of individual people. And then line 8 uses the function counts um, from the states base package to count how many times each birth date occurs in birthdays and assigns these counts to the new array day counts. Okay, then like it is assigning these counts to the new array day counts. Okay, so the logic can be thought of as follows. If two indices have the same value, okay, then this represents two people having the same birthday. And then line 9 checks the array day counts. And if the maximum value of the array is greater than 1, means like that means like if at least two people share the same birthday, then like it will return true, otherwise it will return false. And then line 12 defines the function prob prob est, which like when given n number of people uses a comprehension to simulate capital N rooms. Okay, to simulate capital N rooms, each containing a small n people. So for each element of the comprehension, that means a room, the BD event function is used to check this BD event function is used to check if at least one birthday pair, okay, exists. So then for each room, the total number of at least one birthday pair is summed up and divided by the total number of rooms, capital N. So for large capital N, the function prob est, okay, will be a good estimate for the analytic solution of finding at least one birthday pair in a room of small n people. And then from line number 14 to 17, it evaluates the analytic solution of finding at least one birthday pair in a room. No, sorry. Yeah, so from line 14 to 17, it evaluates the analytic solution over the grid X grid and prints the maximal absolute error between the solutions. Then the output shows that the numerical error is negligible. And then again, the line 28 evaluates the Monte Carlo estimates. And then from line 20 to 27, I plotted the analytic and numerical estimates of these probabilities on the same graph. So here it is the analytic and numerical estimates of these probabilities. Okay, so it was all about birthday problem, and now I will talk about now I will be fishing with and without a replacement. Okay, so let's say if you are trying to do sampling with and without replacement. So in this case, consider where is that example? What was the file name for that? SQSCD, no, buffer feast, random box, polyroutes, occurrence problems, linear classifier, histogram generate. Yeah, here it is. So here what I'm trying, let's consider a small pond. Um, Let's consider a small pond with a small population of 7 fish, okay, three of which are gold and four of which are silver. So now say we fish from the pond until we catch 3 fish, either gold or silver. So here, like the GN denote the event of catching and goldfish. So it is clear that unless n is equals to 0, 1, 2, or 3, so probability of GN is equals to 0. However, so like what is the probability of GN when n is equals to 0, 1, 2, 3? So that's the problem we are trying to solve here. So before continuing, so I want to make a distinction between two sampling policies. So these two sampling policies are catch and keep. So in catch and keep, like I am sampling from the population without replacement. So that is whenever I catch a fish, so I am removing it from the population. And the second sampling policy is catch and release. So in this case, I am sampling from the population with replacement. So that is whenever I catch a fish, so I return it to the population before continuing to fish. Okay. So in this case, the computation of the probabilities, basis probability of GN for these two cases of catch and keep and catch and release may be obtained by hypergeometric distribution and binomial distribution respectively. So these are if you will have any idea about probability, and then I guess you may have studied about these two distributions, hypergeometric distribution and binomial distribution. So now I will directly jump to the code, and now here I will explain what is going on here. So first, let me run all the blocks here. Okay. So now let's talk about code blocks which I have used here. So here from line 3 to 32, from number line 3 to 32. Okay. I define the function proportion first. Okay, which takes five arguments: GF, SF, and N capital N with replacement. Okay, so then here the number of goldfish in the pond is GF. Okay, and the number of silverfish in the pond is SF, and the number of types we catch of fish is N, and the total number of simulation runs which is a capital N, and a policy of whether we throw back or replace means replace is caught fish so which is a with replacement which is set to false. Okay, by default. And from in line 4 to 16, I created an inner function which is fishing that generates one random instance of a fishing day, returning the number of goldfish caught. Okay, and then the line 5 generates an array. The line 5 generates an array where the values in the array represent fish in the pond, with the zeros and ones representing silver and goldfish respectively. And if you will notice the use of zeros and ones function each with the first argument. Okay, and here in 64 is indicating the Julia type. Okay, which we have discussed previously in the type section. And then again line 6 here initializes an empty array which represents the fish to be caught. And from line 8 to 14, from line 8 to 14, it performs the act of fishing n times via the use of for loop. Okay, and then line 9 to 10 randomly it randomly samples of fish from our pond and then stores this in value in our fish caught array. Okay, in value in our fish caught array. And then line 12 here, line 12 is only run if false is used, in which case I removed the caught fish from the pound via the function delete eat. Okay, note that technically we don't remove I don't remove the caught fish. Okay, but rather a fish with the same value 0 or 1 via find first function. Okay, so now our use of this function returns the first index in pond with a value equaling fist. Okay, and now line 15 is the implicit return statement of the function fishing and is the sum of how many goldfish were caught, since goldfish are stored as ones and silverfish as zeros. And then again line 18 implements our chosen policy capital N times total. Okay, with the total number of goldfish each time stored in the array simulations. Okay, stored in the array simulations. Okay, and then again line 19 uses the count function to return the proportion of times 0 to small n. Small n goldfish were caught. And line 21 to 31. Line 21, 31. Then I used a plot function to return the proportions of times 0 to n goldfish were caught. And then in line 21 to 31, then in line 20 to 31, I used a plot to overlay the existing plot with the probabilities. And then the proportion fist function is then called twice in line 37 and 38 to generate the resulting plot. And here, as you can see, the resulting plot. So it was all about our fishing problem. And now I will pick a problem. Now I will directly jump to the machine learning section. Okay, because now we are running out of time. We have around 20 minutes, and in these 20 minutes, I want to cover some machine learning examples as well. Okay, first, which example should I use? Let's use this one. Dense convolutional. Okay, so in Julia, for machine learning, there is a library named as flux.jl. Okay, so here I am using only flux.jl. And if you will see these examples, so in these examples, everything is written in pure Julia. I am not using any Python code or C or C++, except these two examples using Python or using R. Okay, and the meaning of this, I am just implicitly calling these three functions, okay, inside Flux library. Okay, so don't be confused with this thing. By the way, there are a lot of things to discuss about in probability as well, like this is a probability distributions, and there are many interesting problems. So when I will find some more time, then I will try to cover those topics as well. A very interesting test is like the Wolfish runs test. It is also very interesting. Uh, I have not added any recursion example here, right? Uh, Sorry, it was my mistake that I did not add. So I guess you will have a basic idea about training a test or validation splitting things. So I will not cover these things. I will just directly to the examples. Yeah, so here in this example, if you will see, okay, here I used the flux.gel package. Okay, so the key lines defining the mathematical structure of okay and line. Okay, before it, I have a very simple example as well. Where it's that example, not about uh, is it linear classification? No, occupancy problem, plot sample, random box, SQST using plots, independence histogram, Luxatum regression. Ad hoc chain stationary times convolutional dropout. I have not added the MList example here. Okay, so right now I will talk about this ad hoc problem directly. Okay, so like here like oh not now. So in this problem, what I am trying to do, so here I used a library called ML datasets, which is consisting some datasets inside this library itself. So I'm using this library and using a function like using this ML datasets.mnist, I can directly call the data here. So I don't need to add, I don't need to read or something like this. Okay, so here I use the ML datasets package to obtain the MNIST data, as you can see here. This differs like so in line 3 to 4, I retrieve the data into xtrain and xtest in the form of a three-dimensional tensor. Okay, in the form of three-dimensional tensor, and I then put it in the form of an array of image, also transposing. Okay, so then again in line 6 to 7. Okay, then in line 8 to 9, then lines 8 to 9 break up the training data into positive examples and negative examples. And then line 12 to 20, I implemented peak prop function like as described above. And if you will note that like in line 16, if the index of the maximal row pixel m is not in the range 3 to 25, so I use continue to jump to the top of the loop for the next iteration. So the accumulation of pixel intensities is in line 17 and in line 19. After iterating over all row j, I return the proportion, and then in line 21 I implemented the predict function. Okay, then in line 22 to 31, I implemented the F1 value function for assessing the F1 score for a given theta value. And then line 33, it broadcasts a peak prop function on the positive training examples and the negative examples for the purpose of creating the data for the left hand plot. Okay, and now lines 35, the line 35, it creates F1 values, which is used for the right-handed plot. Okay, and then the optimal theta threshold is found in line 37 to 38 and printed in line 39. The remainder of then this remainder of the code creates the figure. So now let's run this example. Uh, so it is running just these blocks. Okay, it is asking. So let's wait until it is finished. Till then, I will open this folder. Okay. Bubble sort. Oh, I will have to run this one again. Anyway, I will also add all these examples in my GitHub repository from where you guys can access these examples and try to run and try to use these examples in your own environment. So let me do this in a few seconds. And then it's running. So let's call a new directory name, new repository name. And now let's clone it. I will need a So where I stored CD Chile workshop. Okay, and now let's put all these examples inside this. Okay, now check the status. Get status. Get commit. Oh, first we have to add all the files. Then git commit and I push all the examples here. Yes, so now I have posted all the examples in this repo. So now you guys can access all the examples like whatever I have, and I have added the dependencies as well for all these examples. So what you can do, you just need to clone this repo, okay? And after cloning this repo, just go to inside that repo, and after going inside this repo, just give a command named Julia, and after giving a command named Julia, activate the environment for this repo. Okay, no, not for this repo. Go to the inside a folder, Julia workshop. Okay, and then open your Julia terminal and activate it. Okay, now if you will give a command status to check the status of any like package, like what package you are having inside this environment. So as you can see here, these are the package, but these are not installed. Okay, so how we can do this? Just you have to give a command instantiate. Okay, yeah, instantiate. When you will give this command, instantiate, then it will install all the packages like whatever it is having inside the project .toml file inside this file. Okay, so just in a single command, it will install all the packages, and after installing these packages, then inside that and environment, you can run all these examples which I have discussed here. So that's all for today, and I guess now it's the end of the our 3 days workshop. So during these 3 days, I guess we have now covered a lot of topics. Now, if you guys will put a little bit effort from your side, then you guys can easily a lot of things in Julia. And after learning these things, I always welcome to all of you to contribute in the Julia community. And to contribute in the Julia community, let's say if you are targeting to contribute in a Julia project itself. Okay, let's first talk about this annual PDA project, which comes under SciML organization and which is about physics informed neural network and deep BSC solvers of differential equation for scientific machine learning. Okay, so what just to have to just go to the issues, and if you found any interesting issues and then try to solve those issues, either you can do one more thing, you just go to the labels and try to the search and good first issue, then you will see these are the good first issue which has been opened by the maintainer of this repository. So just click on this issue, and if you are able to understand this issue, then try to solve this particular issue, and then you are good to go. And through this way, you can make your presence in the open source. And when you will practice a little bit more, then I guess slowly, you will be able to solve some hard level issues as well. So it was all about Julia. Okay, and now I am hoping you guys now will try to do some things on your own. Okay, so let me drop the repository link where I have published all the codes. Yeah, so it is the link using which uh, you can access all the examples. Okay, so about certificates, the Floxus team will automatically send you the certificates in your email, registered email ID, from which you guys have registered. And if you guys will have any answer, will have any questions, then you can connect with me using LinkedIn as well. And I guess you can connect with me, you can contact me on Julia Slack channel as well, where my username, where if you will search something like this, Rohit Rathor 1. Okay, then you can find me using this username on Julia Slack channel, and on LinkedIn you can also contact me, like if you want, if you want to know further, how you should increase your learning in Julia. Okay guys, thank you so much for attending this session. Bye bye, take care.